Hello everyone, my name is Lisa, and today I'll be discussing the paper called Squid Enabling Search in DHT-based Systems by Cristina Schmidt and Manish Parashar. Uh, this paper addresses the challenges of flexible searching in distributed hash tables, and it introduce a new solution called Squid to overcome these limitations. As we all know, distributed hash tables play a crucial role in distributed computing by allowing efficient data lookup across nodes. However, they traditionally only support exact matches, which means that to find the file or data point, users must know its exact identifier. This limitation restricts users who may want to find specific node using different keywords or partial naming or ranges. So, for example, to find nodes that start with specific name, with specific letter, with specific bit, and so on, which makes DHTs less flexible for broader search requirements. So the Squid paper introduces a novel solution to this problem by enabling flexible search capabilities within DHT systems. Squid's purpose is to support a wider range of queries like range searches and approximate matching, so users can discover data more intuitively across large decentralized networks. And that's how Squid overcomes this limitation of DHTs, but still be very flexible and not losing any speed or scalability of DHT. In order to understand how Squid works, let's look at the architecture components of the Squid. First one is dimension reducing locality preserving indexing scheme. Structured overlay network, mapping from indices to nodes in the overlay network, load balancing mechanism, and query engine. To enable flexible searching in distributed systems, Squid constructs an index space using the Hilbert space filling curve. And this is how it works. Firstly, data in Squid is represented in a multi-dimensional keyword space where each data element is associated with a specific keyword that serves as coordinates. It is exactly our attribute-based naming technique from the textbook that we know. So if we want to identify a specific node, we don't identifying using one ID. We identify it using 3 attributes or more, or 2, saying like department ID, ID of this specific computer, and some other attributes. This means multi-dimensional keyword space. This layout ensures data locality. For example, 2 keywords like computer and company, which are geographically close, will also be near each other in the keyword space. To efficiently map this multidimensional data to a one-dimensional index, Squid is using space filling curve, specifically Hilbert curve, which continuously traverses this multidimensional space and preserves locality. This means that points close together in the multidimensional space will stay close in one-dimensional index too. So it can be observed here on the figure 3, how we go from first order Hilbert curve, second order Hilbert curve, and third order Hilbert curve. This locality preserving property of the Hilbert curve allows Squid to handle complex queries involving ranges, wildcards, and partial keywords with fewer node lookups, making it very, very efficient. Now let's discuss how Squid maps data indices to network nodes and process user queries efficiently. In Squid, data elements are first indexed using the Hilbert curve, creating a one-dimensional index. Each node in the network has a unique identifier within a circular identifier space, as seen in other DHT systems like Chort. And when data element is added to Squid, its index is mapped to the first node with an identifier equal to or larger than this index, and this node is called successor of the index, the same idea as we also saw in Chorts. So basically, there is a 2-dimensional space, storage space, and base bandwidth. Using the Hilbert curve, we create these identifiers 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on until 63, which can be placed on this circle. And all of them, all of these numbers are the same as here. So if we need to map 7, how it works, we put it on this one-dimensional space, and then it's mapped to our successor, which is 13, because it's the closest, largest node. The query engine processes user queries by translating them into cluster within the index space. For example, this simple query points to a single location, while complex queries like those with ranges and wildcards identify clusters in the index space. So here, we want to show 2 types of queries that can be processed using the Squid, which is this clusters. It's the range from all points from where x-axis is a star, which is like all points, and y-axis is just 4, and another range which is specified here, and it's going to be identified and mapped to the one-dimensional space like this. Once the cluster is matching the query identified, the query engine routes the search request to each relevant node. Nodes use a cluster prefix generated by the space filling curves, digital causality property, to direct the query message to the appropriate nodes. And this approach makes query processing efficient by ensuring that only relevant nodes are queried, reducing unnecessary network traffic and enhancing scalability. So basically here for this region, for example, region from star to 4, so for x-axis, this gray region, is going to be mapped in these areas, but it's going to be mapped only to nodes 33 and nodes 47, even though it shows like 3 small areas, so we're not sending too many messages. Now let's talk about how Squid optimizes query processing to handle complex queries more efficiently. When a query is complex, such as using wildcards or ranges, wildcards is this thing, it generates many clusters. Without optimization, each cluster would need a separate message, which isn't scalable, and Squid solves this with recursive cluster generation, an approach based on the recursive nature of Hilbert curve. Using the digital causality property, Squid refines the cluster progressively, and each level of refinement generates a longer cluster prefix, which helps group cluster by their prefix. And in the recursive process, each node in the network acts as a level in a tree, refining clusters further and forwarding subqueries down the tree until they reach the nodes containing the matching data. So this is all the same process that is shown A, B, and C, just showed like in different visualizations, but this is the same process of recursive refinement of the query 0, 1, 1, and all of other nodes on y-axis. So basically, when we increase the order of the Hilbert curve, which is going to be this areas, smaller and smaller areas. And this is in the visualization of tree, and this visualization of on the circle. So this figure shows this query refinement as a tree and how it's going to be mapped to the overlay network. The root node performs the initial refinement, passing some queries to nodes that handle further refinements, and this reduces the number of messages and focuses the query process on only relevant nodes. If a cluster matches a node's prefix, it stops refining and processes the query locally. And this optimization minimizes the messages needed, distributes the query load across multiple nodes, and keeps query resolution scalable even for complex searches. Now let's wrap up and go to the conclusions of what authors achieved. The key achievement of the Squid system is that they introduced flexible search capabilities in DHT-based systems, enabling range of queries and wildcards and partial matches. Squid optimized query engine and ensures that even complex searches are processed efficiently by minimizing messages and distributing query loads across nodes. This innovation efficiently addresses the limitations of traditional DHTs. Speaking of contextual significance of the paper, when the Squid was introduced, it was in 2008, and DHTs were widely used for peer-to-peer applications, but they were limited to exact match lookups, and Squid actually resolved this problem. It contributed directly to this constraint. It allowed DHT to support complex searches, and of course, this made this paper very popular, and it has lots of citations too. The authors Cristina Schmidt and Manish Parashar are recognized for their work in distributed computing, and Squid has influenced both academic and practical developments, and its principles are still visible in modern decentralized systems like blockchain and other systems where flexible data discovery remains very essential. As my personal opinion and possible questions, I really like this paper because it represented a practical solution to a significant limitation in traditional DHTs. And the paper takes a fresh approach by enabling flexible, efficient searching techniques. A possible limitation actually that Squid may have is that it was tested primarily theoretically, and it would be interesting to see how Squid performs in environments with fluctuating network loads or rapid node changes. And as to the questions that can be asked for this paper, first one is how could Squid indexing systems adapt to real-world network fluctuations more efficiently? Are there optimizations that could make Squid even more resilient to rapid network growth? And how well does Squid handle very high dimensional data spaces? And that's all. Thank you so much for listening. Have a good day.